Welcome back. So we're in the midst of examining dynamics from the point of view of the chemical master equation. What we've just done is we've taken on the relatively simple case of using the chemical master equation for thinking about the constitutive promoter. That is to say, a promoter which we think of as nothing more than a factory. It's just constantly spinning out mRNA at constant rate R. Now what we're going to do is we're going to tackle what, for now, at least up till this point in the course, is likely to be the most technical of the calculations. And my plan is to break it up into several parts. The first part will be primarily focused on intuition and how one handles the equations. And then the second one will be on the actual derivations. But I've pre-written it because it's a mess. And I'm mainly giving it to those of you that want to see the details and not necessarily suggesting that, that you watch it, although I think it's quite fascinating, to be honest. Okay, so what is the first thing I want to say? The first thing I want to say, this is work from Ido Golding from early 2000s, and very beautiful and super provocative and kind of paradigmatic study. And what Ido was telling us is that transcription does not look like the steady state mRNA factory that I just described a minute ago. So this notion that the mRNA is being churned out at rate R is belied by data like this that shows we have periods, indeed, of churning out mRNA at some rate R, let's call it, without being too fixated on, is there some nuance there, but then punctuated by periods of stasis where nothing is happening. And so this is often referred to as Bursty transcription, and this is not consistent with the Poisson model that we wrote down a few minutes ago. And I alluded to this earlier in the context of the work of Zenklusen and Singer. I've already shown you this work on the left, and we showed it to celebrate an example of the Poisson distribution. But on the right, you see that this thing falls on its face. In other words, for this particular gene on the right, the data is manifestly not Poisson. How do you know that? Remember, the scheme here is that you can find the average of your data, and then that's the end of that. Because once you know the average, the Poisson distribution is the Poisson distribution for that given average. It doesn't work. And so what we're going to do now is we're going to have a shift of mindset. And what we're going to do is we're going to talk about a super important paradigm all over the place, whether in the biological setting or in physics, and that's kind of the power of two-state thinking. So already in the context of the Monod, Wyman, and Changé model, I gave you an example of two-state thinking where we imagined macromolecules such as enzymes to exist in two states, an active state and an inactive state, and there's some effector that binds to the enzyme and alters the relative equilibrium between those two states. So now we're going to be even more abstract, because what we're going to do is we're going to imagine our promoter of interest, that the promoter which is the basis of the synthesis of some gene of interest, that our promoter of interest switches back and forth between an on state, which we signify here by a polymerase, but we're not making any particular molecular commitments. And over here we have the off state, and also again with no particular molecular commitments. When in the on state, RNA is produced at a rate R. When RNAs exist, they're degraded at a rate gamma. And that is our model. That's it. Now, this tells us right off the bat that we're going to have to be more nuanced in our treatment of the equations of motion. And the reason I say that is that I'm going to acknowledge two distinct probability distributions. One of them is the probability of a cell being in the active state, and harboring mRNAs. At time t. And then the other one, I'm just going to copy it. The other one is probability of being in the I'll use red to really make it clear, being in the inactive state and harboring mRNAs at time t. So the point is that since the cell, a given cell can at a moment t either be active or inactive, we find it advantageous to treat those two situations as distinct. So, so that's the basis of what I want to try to think about. I want to just give you a sense of the parameters in this two-state model. So the time scale that it stays in the active state, shown here, is roughly 1 over k off. Because k off, remember, is the k off delta t is the probability in a given instant delta t that the promoter will go from the active to the inactive state. So basically, once you know that, then 1 over that rate parameter gives us the average time, or an estimated average time, to exist in that state of interest. Then there's also a separation time, or I would think of it as the waiting time, which is 1 over k on. So in other words, the bigger k on is, then the shorter time we wait until we'll jump back into the active state. So this is the time scale of waiting in the inactive state, and then the amplitude r is basically telling us how much oomph we get out of a given period of transcriptional activity. So those are the parameters of interest in this case. So here's the kinetic diagram. If you think back to the chemical master equation, then you'll recall that the protocol for chemical master equations was we need to identify the kinetic states, the states and then the kinetic processes that connect them. And what I hope you can see here is that we have all these nodes in this abstract space. So this is the node with no mRNAs. This is the node with one mRNA. It's 2, 3. But for the system to be in the inactive state. Here this is the node that corresponds to no mRNAs and in the active state. This is the node that corresponds to one mRNA but in the active state, and so on. Note the transition rates. To go from 0 to 1, how do I go from 0 to 1? I'm active. And so I create a new mRNA. So there's an arrow in that direction. If I'm in the 1 state, I could become a 0 while still active by having an mRNA degrade. Notice up at the top that all these arrows point only to the left, and that is because that an inactive state cannot move to the right, because a 1 cannot become a 2, because it cannot synthesize mRNA when it's in this inactive state. And then these parameters are the switching rates between the inactive and the active states. So that's the starting point. Now let's see if we can, by scratch and sniff, if we can write down the equations that describe the dynamics. I'm going to actually favor writing the A equation first. So a given node in A, it can first of all, so this is by dt, it can actually become an inactive state. So that would be PA of M and T. And if I'm currently inactive with mRNAs, then I can increase the probability of being P active if that transitions from inactive to active. Then I have to account for the various ways that I can change the numbers. So I have a K on, and that comes from PA at M minus 1. And I have a minus K on PA, and that corresponds to being an M now. So I will leave my current value if I currently have M mRNAs and I transcribe in the next instant, I become an M plus 1. So that means I decrease the quantity of M. Then I can also be an M plus 1 and active and decay and become an M. And finally, and that increases them, and then finally I could be an M and decay and become an M minus 1. So that is our equation, of our dynamical equation for the active state. The inactive state is similar, but simpler. So the first thing I'm going to do is I will copy these first two terms and bring them down, but I need to change their signs. Why do I have to change their signs? Well, because if I'm active and I become inactive with rate k off, this thing, I increase the number of inactives. And here, if I'm currently an inactive and I become an active, then I'm going to decrease the number of inactives. And then I need to consider the decay terms. Oops. So here I have these decay terms, but once again I have to be careful because these apply. These apply to inactive. So those are my two equations. I have two equations. Well, actually, now I have two equations describing active and inactive, but there's one such equation for every value of m. So in fact, I have tons of these equations, and so that's fine. So the last thing I want to say in light of this particular analysis, I want to give you a sense of where we're going to go with this. So, you know, I've talked in the past about, in theory, we often want to calculate what people have measured. And one of the things that people have found it convenient to plot experimentally is what's called the Fano factor. So the Fano factor is defined as the variance divided by the mean. I already talked about this, but for Poisson, Fano factor is equal to 1. And so this is a statistical quantity that we can appeal to make contact with experimental measurements. So more broadly, what I would say is that, you know, if you look back in the notes, you'll see that I have this vignette about every distribution has its moments. So we are going to want to calculate m to the 0 power, m to the 1 power, and m to the 2 power, the 0th, 1st, and 2nd moments. And I'm going to assert that m0 is equal to ma0 plus average of mi0. I will come back to that, but this is essentially the normalization condition. What do I mean by this? So what I mean by the notation is these two guys, this and that, are the partial 0th moments. What does that mean? Well, remember, if I have my system, it can either be active or inactive, and the 0th moment is telling me that the probability of something happening is 1. But it doesn't say the probability of being active is 1, or that the probability of being inactive is 1. So the guy on the left, this one, that's the probability of being active. How do you get that? You get it by summing over all m. This is the probability of being inactive. How do you get that? By summing over all m for the case of pi. So let me just be clear about that. So what I'm claiming is that ma0 is equal to sum over all m from 0 to infinity of m times p(a) m. No, sorry, I don't need that m there. That's completely wrong. Excuse me. Once again, I got too enthusiastic and got ahead of myself. Okay, so that's what I mean by ma0 and mi0, is given by sum m equals 0 to infinity of pi of m. So what does this mean? This is telling me, hey, doesn't matter whether you have 0 mRNAs, 1 mRNA, 2 mRNAs, etc. What matters is, are you active? What's the probability of being active? And the way you find that is you sum over all the favorable events, which is all of the active state for different numbers of mRNAs. Okay, so that's one of the things that we're going to interest ourselves in. The first moment, M1, that, as I said, was equal to MA1 plus MI1. And now I'm ready for my enthusiasm. So this one is equal to sum m equals 0 to infinity of M P A M. And this one is equal to sum m equals 0 to infinity of M P I. And we can do the same thing for the second moment. So I think this is basically where I want to stop for this introduction. Let me foreshadow, just in case you're wondering whether you want to tune in for the next bit, and maybe I'll say a word about the experiments. What I'm going to do is I'm basically going to walk you through how in steady state to find the 0th, first, and second moments, and from them, the Fano factor. Now, I wouldn't say the problem with that, but the reality of that is that we have to do quite a bit of calculating. And I could do this in real time, but in fact, what I think I'm going to do is I'm going to show it and illustrate a few of the highlights and leave it to you as something that you can pursue yourself if you want to go through the details, okay? So let me just comment on where this all goes, because I've brought up this idea of closing the loop before, and I want to make sure that it's clear that we're interested in closing the loop. What that means in particular is making contact with experiments, and the kinds of experiments that test this two-state model that I'm mentioning are shown here, where what's plotted on the y-axis is the Fano factor, so this is a measure of the noise in the gene expression, and on the x-axis is the mean mRNA copy number per gene, and the two different curves, the red and the green curves, correspond to different promoter strengths. And so basically by tuning the knobs using molecular biology, one can span this space, and those red and green curves are parameter-free predictions of this two-state model for the noise and gene expression in a particular realization using the lac repressor. So that's where we are on this particular case study, and in the next vignette, what we'll do is we'll go through the actual mathematics.